part A, we want to find f of g of x and its domain. So a reminder, when we have the open dot notation, the way we read this, we can read it as f of g of x, or you could say f composed with g. And a second way of writing this would be to write it with parentheses. It would look like this, f of g of x. And most people prefer this second method because you can clearly see which function is on the inside. So this is telling us we're going to take function g, which is this function 5 divided by x, and it's going to become the input. We're going to substitute it into function f everywhere that we see or have an x. So every x in the function f is going to become 5 divided by x. So this looks like 2 times the quantity, but in place of x, we're substituting in 5 divided by x, all divided by, instead of x minus 1, it'll be 5 over x minus 1. So now we just need to do the cleanup algebra, allowing us to simplify here. So in the numerator, we're going to just multiply. This is 2 over 1 times 5 over x, so that's just going to be 10 divided by x. Remember, when we multiply fractions, we're just multiplying the numerators and then multiplying the denominators. But down here in the denominator, I have 5 over x minus 1. So I need to actually subtract fractions, which means I need to get a common denominator, or a least common denominator, an LCD, between x and 1. So my common denominator is going to be x. So you'll notice that the first fraction, the 5 over x, is good to go. It already has the denominator that we need. But my second fraction, I'm going to need to multiply the numerator and denominator by x. So we're multiplying by x over x. So we end up with 5 over x minus x over x. So we have our LCD now, and we can go ahead and subtract. So I'm cleaning up this denominator here, and 5 over x minus x over x is just going to be 5 minus x, the whole quantity, divided by x. So we're calling this a complex fraction because we have a fraction within a fraction. So if I use some parentheses here to show you the difference, 10 over x is in the numerator, and 5 minus x divided by x is in the denominator. So remember, we do not divide fractions, but rather we multiply by the reciprocal. So we're going to have our first fraction, the numerator, which is 10 over x, but we're going to change the division, and here's my division right here in orange. This is my division bar, but I'm going to be changing that to multiplication by the reciprocal. So I'm going to take the reciprocal of the denominator, which would give me x divided by 5 minus x. Now I have a multiplication problem. We're just multiplying two fractions. And I could go ahead and multiply the numerators and multiply the denominators, but it's probably going to be easier to simplify first. So I can simplify because I have x in the numerator and x in the denominator. So that's essentially x divided by x, which is the same as just 1. So we can divide out the x in the numerator and the x in the denominator. So I'm left with 10 divided by 5 minus x once we simplify completely. So we can say that f of g of x, which is what we were originally asked to find, is equal to 10 divided by 5 minus x. So this is the first part of the problem, which was to find the composition. But you'll notice it also asks us to find its domain. So when you're working on the domain of a composite function, you're going to need to consider two different parts. First, just look at the result here, my composite function, which is 10 divided by 5 minus x. So just thinking to ourselves, what are we allowed to have or not allowed to have for x? Well, this function contains a fraction, and we know that in a fraction, the denominator here, the denominator cannot equal 0. So you're just thinking to yourself, what would cause the denominator to equal 0? Or if you actually want to do the algebra, the denominator is 5 minus x, and we cannot have that equal to 0, so we need to solve this equation. And once you solve this equation, you'll see that x cannot equal 5. If x were to equal 5, we would have 0 in the denominator. So that's going to be the first value that is a restriction, a value we cannot have in our domain. So we write x such that x cannot equal 5. However, if you go back to the beginning and take a look at the way I wrote the composite here. Without the open dot, I wrote it with the parentheses f of g of x. And remember which function was on the inside. I underlined function g because g of x was the function that became our input. So we also need to consider any domain restrictions in function g because that's the function that we started with. So take a look here at the very top at function g, and you see that g of x is equal to 5 over x, so we definitely have a restriction here. We cannot have 0 in the denominator of this function. So we need to go ahead and include 0 as our second domain restriction. So again, we're getting the 5. 5 is our domain restriction from our simplified answer for the composite function f of g of x. But we have to include 0 because 0 is the domain of what I call the inside function, the function on the inside, which in this example was our function g of x. So 0 was our domain restriction in the inside function. Always want to include the domain of the inner function. So very quickly before we move on, I want to kind of show you why these two values cannot be included in the domain. I want you to actually see why they don't work. So let's say, here's my two functions. I just wrote down this as a check. Let's say I wanted you to find f of g of 5. 5 was a value that we just said is not in the domain. So let's actually compute this and see what happens. So if we start on the inside says we have to compute g of 5. So g of 5 is going to be 5 divided by 5, which is 1. So this inside piece, g of 5, is actually equal to 1. So now I need to take 1, and 1 becomes the input in my function f. But in function f, if I input 1, look what happens. 2 times 1 divided by 1 minus 1. We end up with division by 0. So see, this is why 5 is a value that is not in the domain of the composite. Now let's do a similar check for 0. We said 0 was another value that we cannot have in the domain of this composite. So let's go ahead and compute f of g of 0 and see what would happen. So starting on the inside asks us to compute g of 0. That means we're substituting 0 into function g, which immediately gives us 5 divided by 0, which is undefined. So you can see right away why 0 is not in the domain of the composite, because 0 is not in the domain of that inner function that we would be starting with. Part B, we want to find g of h of x. So remember, if I rewrite g of h of x, another way of saying that is g composed with h. I can rewrite it as g with parentheses and h of x here on the inside. So we can see that h of x is my inner function, or h of x is what I'm going to be substituting into function g. So again, if I take a look at function h up here, here's function h, and I'm going to substitute that into function g everywhere I have an x. So that means I'm going to have 5 divided by, but instead of x, I have my function h here in the denominator, which is the square root of x minus 6. So this is a nice fast one because there's no simplification to be done. There's no algebra here like there was on our previous example. It's just going to be 5 divided by the square root of x minus 6. So that's it. G of h of x is equal to 5 divided by the square root of x minus 6. And then we get to move right on to the domain. So we start with just the domain here of the composite. So we have a fraction, so we know that we cannot have 0 in the denominator. But in addition to this, we have a square root. So we have an additional restriction because we know that we cannot have a negative inside of a square root. So we kind of have a double whammy. We know that the inside of that square root cannot be negative, but in addition to that, we can't have 0 because we can't have 0 in the denominator of a fraction. So we could write it this way, that x minus 6, which is what's inside the radical, that's called the radicand, it must be greater than 0. In other words, it must be a positive number. It cannot be negative, and it cannot be 0. So solving this tells me that x must be greater than 6. So that's the beginning part of my domain. But then I also need to go back and consider the inner function in case there are any restrictions. And my inner function here was h of x. So looking up here at function h of x, we notice that it also is the square root of x minus 6. So if we were to compute the domain of function h, we would say that we cannot have a negative, but we could have 0 or a positive. And so the domain of the inner function is x is greater than or equal to 6, which you'll notice matches what we have, only we have to make sure that we don't include 6 ultimately in our composite function, because 6 would cause us to have a 0 in the denominator. So basically what this means is that when we considered our function h, it did not give us any additional domain restrictions. Therefore, the domain for our composite is simply going to be from 6 to infinity. Any value larger than 6. So x is any value from 6 to infinity. Part C is asking for f of x. That might look a little odd to you to have the same function here. But f of x, again, you could say that as f composed with f. Rewritten would look like this, f of x with all the parentheses. So we see that f of x is actually my input. So it might seem odd, but we're taking this function f, which is 2x divided by x minus 1, and we're basically going to be substituting it back into itself. So in other words, rather than having 2x, we're going to go ahead and substitute in place of x function f, which is 2x divided by x minus 1. And then that's all divided by, but instead of x right here, that x becomes function f, which is 2x divided by x minus 1, and then we have minus 1. So that's what our initial substitution looks like. So this is another messy one with the algebra because we have a composite function, so it just takes quite a bit of simplification. So once again, let's start with just the numerator. We're multiplying 2 over 1 times 2x over x minus 1. So we just multiply the numerators, multiply the denominators. So we end up with 4x divided by x minus 1. All divided by, and then when I take a look at my denominator here, I'm subtracting two quantities, but one of them is a fraction, so this is back to subtracting fractions. So think of this as 1 over 1. So once again, we have to get a least common denominator between x minus 1 and 1. So my LCD, or my common denominator, is going to be x minus 1. My first fraction is good to go. It has the LCD, but my second fraction I'll have to multiply by x minus 1 divided by x minus 1. So I'm going to do this in two separate steps for you. So now I have 2x divided by x minus 1 minus, and then I have x minus 1 divided by x minus 1. So once again, trying to differentiate the numerator and denominator so you can see the difference. Here's my numerator, and then all of this, here's my denominator, which I need to simplify some more. So once again, the numerator is good to go. It's 4x divided by x minus 1. But my denominator has these two separate fractions. So they both have a common denominator of x minus 1. So then we just want to go ahead and do our subtraction. However, you do have to be careful here because notice it's 2x, we're subtracting, and you're subtracting this entire numerator. So we do have a sign change here because that's going to be a minus x, but then a plus 1 when you're sure to subtract. It's like you're distributing this negative, treat it like a negative 1. So again, simplifying, we end up with 4x divided by x minus 1, all divided by, and then our fraction here in the denominator, once we simplify, 2x minus x is just going to give you x. So that would be x plus 1. So once again, here's my numerator, here's my denominator. But we recognize that we don't want to divide fractions. Instead, we want to multiply by the reciprocal. So we have 4x divided by x minus 1. we change our division to multiplication, and then we're going to be taking the reciprocal here of this denominator, what I'm dividing by, which gives you x minus 1 divided by x plus 1. Now we can do some simplification. Since we have multiplication, we have an x minus 1 that will divide out with this x minus 1 on top. And now we're left with 4x divided by x plus 1. That was a long one. Okay, so we just found f of x, and it's equal to 4x divided by x plus 1. That's our simplified composite function. Whew. All right, so moving on to domain. So once again, we start with just the domain of this composite. So notice the numerator contains an x, but there's no restrictions for the types of numbers you can have in the numerator of a fraction. However, the denominator we know cannot equal 0. So the denominator cannot be equal to 0, so that tells us that x cannot equal -1. So there's our first domain restriction. We write x such that x cannot be equal to -1. But then we have to remember, we just found f of x. So in addition to finding the domain of my simplified composite, I have to also consider the domain of my inner function. And my inner function in this case was f of x. So I've got to go all the way back to the top and take a look at what was our function f of x. And here it is up top, and go, are there any additional restrictions in this function? And we know function f, x could not be equal to 1 because we couldn't have 0 in the denominator there. So going back, that means we have a second restriction here for our domain. X cannot equal -1, but x also cannot equal +1. So again, a recap. The -1, that came from the domain of my simplified composite right here. However, the +1, that was my domain restriction that came here from the domain of the inner function, and the inner function was f of x.